My name is Lafforgue. I'm from the University of Innsbruck in the group of Professor Francesca Faleno, and today I will just contrast a little bit with the previous talk in this section and not talk about photons but more atoms. Um, so yeah, in my lab we use ultra cold atom of erbium. Why erbium? This is a very nice species, even if it's all the bottom at the lanthanide and the electronic structure is very complicated. So what we have is a very rich atomic spectrum with a lot of optical close transitions that we can use for cooling or addressing. I will go a little bit more in detail in my talk. Also, there's a lot of things that are known with erbium and also with dysprosium and this magnetic moment. So you get a permanent magnetic moment in the ground state, and you can do all this dipolar physics. That's not the topic, right? No, that's not the physics of my talk, but this has been done in the last 10 years. And there's a nice property also in erbium is that you see the angular momentum in the ground state is J equals 6. So if you remember, so if you know about your quantum physics class, so it means that you have actually certain spin state in the ground state you can use to do physics with. And so this is exactly how the ground state of erbium looks like. Usually due to magnetic field, we have a Zeeman shift, which means that only one of the state is actually the real ground state. So when you do mod cooling and evaporative cooling, you end up with all your atom in the -6 states, and most of the physics that has been done in the past 10 years was done with this ground state atom. Now, when I arrived to start my PhD, there was the question is, okay, how can we use this very large spin manifold? Which kind of physics can we do? How will dipolar interactions play a role? Scattering. But the first step was actually how we prepare those excited spin states. So the problem is we have two main challenges. Is that there is no nuclear structure, so it's only a Zeeman shift or linear Zeeman shift. So if you want to address a transition, usually you will use radio frequency transitions, and they are actually resonance with all the spin state, and this is what you obtain in the lab if you do Sternegger-like imaging after applying a radio frequency pulse at resonance between the spin levels. And there's another thing is due to dipolar relaxation, when you prepare your atom into excited states, they will naturally want to actually go back to the ground state. It's just due to the permanent magnetic dipole interactions, and this is always there. So to prepare a spin state, we actually need to be faster than this relaxation, and we also need to do something to break this linearity in the Zeeman state. And what we have, as I say, we have many optical transitions we can use, and in particular, we can use a transition at 1299 nanometer, which has an extremely long lifetime, so very long, very small line width, and has a slightly different Zeeman splitting in the excited state. What means is that actually the transition frequency between these states and the adjacent state will be slightly different, around 135 kilohertz per Gauss. So for typical magnetic field in our lab, which is around 1.9 Gauss, we actually get a strong splitting between all those transitions compared to the line width of our light, and we can address individual spin state and actually manipulate the spin. How do we do this? So the first state is actually to bring all the atom to the excited state. So once we got this laser, we just do, we could show that we can get coherent Rabi oscillation, and we are actually able to pump all the atom to the excited state. So what we do is we do a first pulse, we pump all the atom to the excited state, and as the line width is very small, we actually have a pretty long lifetime in the excited state. So we can store the atom for 100 milliseconds. And once we have pumped all the atom to the excited state, we switch off our laser, we apply a second pulse, and then we go down back to the ground state. Typically, so the scale of the Rabi oscillation, so we can do Rabi oscillation at roughly 10 microseconds scale, which means that we are much faster than any other collisional dynamics that is happening in our sample. And so we can do a series of 2 Rabi pulses and then bring all the atoms to the excited state -4. By just tuning how much we transfer from the first ground state to the excited state, we can also control the population. And then once we are in this state, we can actually repeat this process. We can change the polarization of the second pulse. Instead of having sigma minus, we could have pi and again have the atom in the -5 state. And here are some pictures we can have in Sternegger-like. So just to show you that we can prepare more or less every spin mixture we want. So like from zero, so non-dipolar, dipolar, anti-dipolar mixture, and any in between. The full transfer, typically to go from -6 to 0, is around 85 percent efficiency, which is not very great if you talk to someone that does quantum computations. But for us, let's say, to study just interactions between spin is more than enough. So that's this work was published in PRR in 2024. There's a bit more going on, but let me jump directly to the second part of the talk. And the natural question that arises if you are an ultra cold physicist is actually, okay, it's nice you prepare those spin states, but what can you do with them, and especially how do they interact between each other? So that's the thing. The problem is in lanthanide, in erbium, in dysprosium, it has been studied that the scattering, or let's say the interactions between two atoms, just in the ground state is already very complicated and can be proven to be chaotic to some extent. And so, if you add the spin degree of freedom, how can you understand anything? So the first thing we have done is let's say, okay, let's just give it a try. And in atomic physics, or like in ultra-cold gas, we have a very nice tool to try to understand interaction. It's called Feshbach spectroscopy. So we basically prepare our cloud at a certain magnetic field. Then we go very fast to a magnetic field, and we look at how many atoms we have after a certain time t. Usually what you see is you see the appearance of some resonance. That means you couple some to some molecular state, and that indicates you that in those regions you can control the scattering. The thing is, you see there's this background here that is due to actually dipolar relaxation. So I told you like the spin when you are in excited spin state, they actually want to go back to the ground state due to the magnetic dipole interaction. And this is has a non-trivial dependence on the magnetic field as well. So you have this background here when you look. And additionally, you see, so this loss feature, this is what you expect from atom loss spectroscopy. But most surprisingly to us, just already with the first excited spin state, so all the atom into the -5 state, we started to see this very striking feature. So atom loss spectroscopy, usually they are purely Gaussian losses around the resonance. And then you start to see this very asymmetric profile. So what we have done is to look a little bit more into detail into it and say, okay, is it first experimental mistake or not? And no, indeed, if you just do a bit more precise scan of the magnetic field, you see that if you wait a certain time, actually at 0.65 Gauss, you lose less atom than at 0.63 Gauss, and by really a factor of 10 different. We have studied the nature of the losses around this asymmetric line, and then you see it's two-body losses. Same, around the Feshbach resonance, usually what is known is it's like three-body losses. So we say, okay, so that has something to do with like really collisions of two atoms and not just like additional process due to a molecular potential. And then once we can fit with the two body, and we see it has this very nice Fano shape. I don't know if you know, so this is also why they are called Fano resonances. But in the 60s already, Hugo Fano, that introduces this asymmetric line shape, describe it in a completely different setup. But the idea is the following: if you have one atom that can decay to a continuum, or let's say it's a decay ray, and if there are two paths, actually it can go to this continuum. What happens is that those two paths, they can interfere with each other if they have different dependence in the energy, and then they can constructively interfere, so you will have increased losses, or they can destructively interfere, and this is where you have actually so you have a very strong decrease of the losses. So there's almost no coupling to this continuum. So on this, we try to develop a small model that feature a little bit this physics, so inspired by this paper from Hugo Fano. And so let me just briefly recap for those that are not very familiar with what we call like Feshbach resonance, or what happens close to those losses in the Feshbach spectrum. So what happens is actually, imagine now I take two atoms in a -5 state, so they collide with a certain energy, and then if they are resonant with a bond state or with a molecular state, what happens is that they form this molecule, and they can either dissociate and go back to those atoms. If there is no loss rate, so if this molecule is stable, actually they just go from this molecule and then go back. And that's what changed what we call the interaction length, or the scattering length. But now imagine you actually, I told you, the atom, they want to naturally go back to the ground state. So let's say if you start from -5, they want naturally to go back to -6. And so this is just symbolized here in this coupling, this gamma 0. And then what happens is that there are no two paths they can decay. So they can go first, they can naturally decay from -5 to -6. And secondly, what they can do is actually go to this molecular, form a molecular state. And this molecular state can decay in -6 or can choose to go back to -5. So now we are exactly in the situation with this model to the to what was described in the initial paper from Hugo Fano. And then we try to just put some realistic parameters on this model. I mean, this square model is very far from what is really happening with lanthanide atom colliding. But let's say we try to put some parameters and we fix the size of the square well by the dipolar lens. And what we see is actually a very nice thing is that, okay, when you get that resonance, so this is what will happen if you change the magnetic field. So the levels, they will evolve differently with magnetic field due to the Zeeman effect. You get a first crossing of the -6 with the molecular state. Nothing is happening, just the scattering length is changing, because you create a molecule, then you go out again, and then this changed the scattering length. And then when you get the -5 getting at resonance with this molecular state, actually you see also a change in scattering length, but the cross section, the last cross section, which is basically the probability to start from this level and go to the -6, is actually as also this asymmetric line shape. So this was already, okay, that's the physics. We are going to the right directions. And then you can actually very nicely, with just this square wave model, fit again the data. So that's the atom number, and that's the two-body decay rate. So this model was done in collaboration with Meta and Seth Rittenhouse from the US, where they had already first paper that we adapted to our model. But now there's still a remaining question: is, okay, like I told you, we create a molecular state, but what is this molecular state? How does it evolve? What are the quantum number of this state? And that's what we had a look a little bit at. So that's, until now we focus only into the collision of -5 with -5 atoms, but actually I told you we can create any spin mixture. And so we started to do all possible combination of spin mixtures, making a flashback spectrum of them. So here I show just increasing number of things, so -5 plus -5, -4 plus -5, and so on. So we label them after as a total MJ. For example, this will be total -11, -10, -9, and so on. And what you see is that actually you always see some resonances within this range of 0.5 to 2.5 Gauss, and then with also this asymmetric profile. And there seems to move slightly with in the position in magnetic field. And actually, if you plot everything into this Zeeman referential, actually you get a very nice line. And that's just giving you how the energy of the molecule evolves of the molecular state evolves with magnetic field. It's a very nice line, so we can say safely that this molecule, if it exists, has a resonance. So we can find the binding energy as the zero crossing and also know the magnetic moment. And now we took our small square well model and we just added all those channels the same way and also fit in the molecular state with those parameters. And what you see is actually all these resonance that are very well reproduced by only this square well model. And you see that the width is also increasing with magnetic field, and that's very nicely captured by the theory. It has this very striking exponential behavior. Even if you fix all the parameters, there is no like spin dependent parameters, and so that's something that it seems to be quite universal in this resonance. Of course, there's many more going on with this resonance. You can see additional resonances that we have not still fully understood, but it's already a very nice physics, and it's really nice to be able to capture the scattering physics with a simple square well model. With this, I would like to conclude my talk. So I show you that we can prepare deterministically a spin composition in bosonic erbium, which was already a good step. And then we started the first investigation of what we can do with those spin mixture. We already saw that there is actually very interesting physics going on in terms of scattering, and we can have them to understand a bit more scattering in lanthanide, and then there's still a little bit to understand. I told you that there's losses, there's the spin realization that wants to bring everything back to the ground state. The good thing we have is that actually we can load the atom in the optical lattice, and then this to some order is drastically reduced as it has been showed already before. And so our next step is actually to load all those spins in the lattices and try to study the interactions in the lattices. With this, thank you. That's the group. And that's the person that worked on the project here in colors, and the two collaborators from the US. And if you have questions, I'm still here.
And indeed, it's time for questions. I see one at the back.
Okay, thank you for your talk. You said that you see two-body losses around the feedback resonances. And you see that because you fit with a two-body loss.
Yeah, this one, you mean?
Are you in a harmonic trap to do so? And if so, are you sensitive to the increase on temperature during the losses?
So yeah, so you see, if you really like look at the width of the cloud during the fitting, as you can actually, so we have done also fitting actually with the temperature together. So, and you see that two body is the one that fits the best. So we try one body plus three body, one body plus two body plus three body, and at the end this was the only two body that fits temperature increase and atom number.
Okay, thank you.
Yes.
So in the initial part of the talk, you showed the transfer from lowest projection to the next one. Is it like exact number state, or is it a mixture of, like here in this picture, -6 and -4, or you may complete transfer?
So we have a, okay, maybe I show the Sterne-Galact picture. So we can really choose how much we transfer to it. So
so it's like stirrup, or
no, it's not. It's not a stirrup because it's like really two sequence of pulses. It's not like the lights are not in the same time. But what we can do is we do a pi/2 pulse. So you have still some atom remaining in the ground state, and then you have some atom in the excited state. And actually, when you do a pi pulse back to the ground state, you project the rest, the atoms that were superposition on the of the ground and excited. You project one part in excited, and you end up with the 50-50 mixture. So what you get in the Sterne-Galact is that at the end your cloud is like either fully into a single spin state, or you get half of your atom in one spin state and the other half in the other one. And
okay, thank you.
Okay, I see no more questions, so we will thank you very much.